Namaste. I thank the organizers for giving me this opportunity to speak on the Madhava's infinite series for pi. Before I proceed further, to introduce you to who Madhava was or the series that he has presented, I just wanted to draw your attention to the problem itself. The problem is essentially to try to find the relation between the circumference and the diameter of a circle. This is all at constant, as all of us know. That ratio of C by D is what is called pi. And the name pi actually comes only in the 18th century. Some people ascribe it to Euler, whereas certain others ascribe it to William Jones, whoever it is. But the point is, so that peripherion is the term, and that in Greek symbol. So if you write, you will have the pi notation appearing as the first alphabet, and that seems to be the origin of that. So that apart, if you just see the history, so before Aryabhata, so you can see, so it starts with Babylonian, and then we have a few other things I have left out. Then we have Sulvakaras, and the table tells you the kind of accuracies to which it have been determined. Aryabhata in the 5th century gives a value which is correct to 4 decimal places. But in the books which narrate the evolution of pi, in fact, there are several books which have been authored, and the pi is described as the most mysterious number also. Anyway, so if you look at the narrative, you will see that they list this Babylonian and they list a few other things, but after Aryabhata, usually you find a jump. The jump from 5th century to 16th century is something which is quite interesting to note. So Madhava is in 14th century. The question is, why is this omission? Is it due to ignorance? Possibly. But then research indicates that it is not necessarily due to ignorance. We will touch upon it a little later. What is the series that I am talking about? So here is the verse of Madhava. Vyase vadihi nihate rupahrite vyasasagarabhihate trisharadi vishama sankhya bhaktam rinam swam prithak kramat kuryat. This is the verse that actually presents the series. The series which you find below. In fact, during his keynote address, Professor Manjul Bhargava was also alluding to this beautiful series. So here the word Vyasa represents diameter, and the word Paridhi refers to the circumference. Rupa is 1. Vyase Varidhi Nihate. Varidhi represents number 4 in Bhuta Sankhya. So you multiply 4 times the diameter. Rupa Hrute, divide by 1. Then Vyasasagarabhihate is essentially once again 4 times D. And then it says in the later half, Trisharadi Vishama Sankhya Bhaktam. You keep dividing by all the odd numbers. 3 is 3, Shara is 5, Vishama Sankhya is odd numbers. So what you find here in the series is essentially the unit fractions of all the odd numbers, but then they are placed one plus the other minus, alternating sign. This is a really beautiful series, and this is the series which actually for the first time gives the exact representation for pi. So it is irrational number, and therefore you cannot write it as ratio of 2. It is also a transcendental number, but this series, which was found in 14th century, more or less does not appear. In the recent time, of course, things have changed, but if you look at the books on history, so many of them do not carry this. Who is this Madhava? Madhava, who gave this series, the verse which I quoted earlier, is something which has been quoted as the verse of Madhava by later authors in the Kerala tradition. So who are the astronomers? So here you find the lineage, which is rare to find. So we have more or less got who are the subsequent students of those teachers. So this is not a comprehensive list, but it nevertheless represents Madhava. We have then Parameshwara. Then we have Nilakantha Somyaji. So who has authored very important works, Tantra Sangraha and Aryabhatiya Bhashya. I'll be quoting something from the Aryabhatiya Bhashya a little later on the same topic, pi. Then we have Jyeshtadeva, the celebrated author of the famous text Yukti Bhasha. Yukti Bhasha, incidentally, is also described as the first textbook on calculus, okay, of late. So many people have done serious research on that, and they believe that this is something which is worthy of being described as the first textbook on calculus. Why? Because the calculus as a subject we know is something which got developed much later, 3 centuries later, but this is something which is much ahead of that, two centuries later, okay, something like that. Now you see, we have the origins of that. See, what one has to understand is this Jyeshtadeva in his Yukti Bhasha, he says, I am essentially elaborating the techniques which have been employed by the earlier mathematicians and astronomers. And that's why, though we place him in 16th century, all that he explains is something which he has got from the earlier. So that is how he says. In fact, this is written as a commentary to Tantra Sangraha. So therefore, this goes much earlier, and we believe that most of the techniques have been shared by Madhava over a period of time. We don't know exactly what got developed at which stage, but the results of Madhava are really striking. So then we have Shankara Varyar, who has written certain important commentaries. I won't elaborate on that. Pudumana Somayaji, and then we have Achyuta Pisharadi. The signal achievements of Kerala mathematicians, there are a few others, but these are most well known. So first one, as you see, is basically the infinite series for sine function, which will be elaborated by the next speaker, Professor Sriram. Then we have Grigonis Leibniz series, as it is called, the quotation mark. It is actually the Madhava series which I was mentioning to you, which was found almost 3 centuries before. Then we also have a verse which is nicely presenting the derivative of sine inverse function, which I will not elaborate. These are some remarkable results. Many of you may be curious to know, how did Madhava arrive at this infinite series? It looks like a very, very simple, right? Very charming series. In the right hand side, 1 by 3, 1 by 5, 1 by 7, 1 by 11. You put all the numbers, it goes up to infinity. So alternating one, you add all the positives, you subtract all the negatives, you will get pi. It looks like, how did he arrive at it? So it's not too difficult for us to understand. If you want to know how it was arrived by Newton, Leibniz, etc., so later, so that may be a little more complicated, whereas the derivation which is presented here is much, much, much simpler. Even from a pedagogical viewpoint, this is something which is remarkable. What lies at the basis of this is essentially 2 facts. Identifying the similar triangles. See, so in fact, identifying similar triangles, you get profound results. So one of them I'll just show you right away. And then you have a certain nice way of summing up things. So these are 2 things which lie behind the derivation of the series. Let us go through this. See, in this diagram, you will see that I have taken 1 quadrant of a circle, correct? 1 quadrant of a circle, and I have drawn a square around that. All that you do is, see, this quadrant of a circle is, suppose C is the circumference of the circle, then the quadrant is basically 3 by 4. Now, what you have done here is to just take C by 8 and then you map it to the top line. So the top line P0 to Pn in the right hand side. So you see, I don't know whether this the pointer, you are able to see, right? So basically what we do is, so this is divided into n parts. So this is 1/8 of this, C by 8. So you divide this into n parts, n is going to be large. Now you consider basically so the line that actually goes from O to any of these points, so you are dividing it into n parts. So any line that you draw from here is basically called a karna. Why is it called karna? Karna is hypotenuse, as it was introduced earlier. So this is a right angle triangle. O, P0, Pi are going to be right angle triangles, and you conceive of n right angle triangles. So this is how, so you can think of, so if there are n divisions, so you can just think of it to be n right angle triangles. Now you consider just some ith part, pi and pi minus 1. So this is ai minus 1, this is b. So you just think of the intersection of this karna with the circumference. This is ai minus 1, this is ai. You consider two consecutive karnas, and then those points are called ai minus 1 and ai. You drop a perpendicular from ai minus 1 onto this line OPI, and that intersects at B and that intersects at C. You can straight away see that OAI minus 1B and OPI minus 1C are two similar triangles. Okay. Now you conceive of one more similar triangle. So then you form this relation. So this you can very easily see. So you are going to play with these two relations, that is all. Then you will get your very, very interesting result. Okay, so what you get is, you are going to see what I'll just tell you. I'll take you to one second. The technique is basically to get an expression for ai minus 1b. ai minus 1b, so when the number of points is going to be increased, what will happen is, this segment will keep on shrinking and they will become very, very, very close to each other. And thereby you will say that the segment can be treated same as the arc itself. This is the technique. Okay. So you are primarily going to get an expression for ai minus 1b, which is an exact expression, and then you are going to sum it up. So this is the principle behind it. So you get an expression for this. Let us forget this. So the argument that is going to be presented here is paridhi khandasya ardhajya paridhyamsha eva. Paridhi is circumference. Paridhi khanda is basically a part of it. Tasya ardhajya means the chord length. So the chord length of corresponding to a segment of the circumference is essentially same as the segment itself. This is the argument that is being given. Okay, this is very simple. The argument is straightforward. So he says that this is what it is. So this is what in modern parlance one can call it as local approximation by linear functions. Okay, so that is all it is. So then it is a little algebraic manipulation which we are going to do. So what is being done is, so here you see you are going to get an expression for the circumference, 1/8 of the circumference, right? C by 8. That is what we showed in the diagram. So the expression turns out to be something like this. Okay, these are karnas. So since the karnas are too close to each other, right? So you can call it as k1, k2 as k1 square or k2 square. So this is a standard thing which we do. So if they are too close to each other, you can either approximate to this limit or to the other limit. So anyway, some discussion is taking place on that also. I will not get into that now. And assume that you are going to call it as k1 square, k2 square and to kn square. Then essentially what you have to do is c by t. There is no approximation till now. You just see. So you have just taken similar triangles, you got this result, right? So you have to basically find a way to sum this. So the Kerala mathematicians found an ingenious way, and they did some algebraic trick which boils down to what one may call as binomial expansion today. So you are going to play with a little bit of algebra, and finally what you will get is, so you will get an expression like this. Don't be worried that there are too many notations. So it is essentially boiling, if you pull this r by n out, what you will see is essentially 1 square plus 2 square plus and so on plus n square. So 1 power 4 plus 2 power 4 and so on n power 4. So they call it as ekad ekottara varga sankalita. Varga sankalita is sum of squares. Ekadi ekottara. Then you have to find out varga varga sankalita and so on. So this is what it boils down to. So without getting into more mathematics, I'll just take you to the final result. So here Kerala astronomers knew this result. So this is an ingenious way of arriving at this. So they say that sum of so I power k means 1 square plus 2 square, you can put anything, right? So k goes from 1 to n. So this is essentially the A discrete version of what you today call as, see, integral x dx is, so x to the 2 by 2, right? Integral x to the n is x to the n plus 1 by n plus 1. So this is essentially the discrete version. So they have got this result, and thereby you get this beautiful series which was given by Madhava, which is ascribed to Madhava rather. Vyase Varijinihate Rupahrite Vyasasagarabhihate Trisharadi Vishamasankhya Bhaktam Rinam Swam Pruthakramat Kuryat. Okay. Okay. I have spent about 15 minutes now. So the last 8-9 minutes, I'll just move on to something which is far more interesting than this. This series that we had is a terribly slowly converging series. If at all you have to use this series to find out the value of pi, you may have to calculate million terms, even to get the accuracy of Aryabhata, 4 digits. So one will not be able to make use of this series for evaluating pi, though it may be a very beautiful result. So what do we do with this? We have got a nice result. What for? I mean, for the sake of fun, I mean, you can have, but if at all you want to use it, how do you use it? That is the question. So they have found another ingenious way, and that method, they call it as Antya Samskara. Okay. So Antya Samskara, which is normally done to human beings, is done for the series also. Okay. So they say that you can terminate the series at any number that you want. All that you had was all the odd numbers, right? If at all you want to find, how will you find? You have to evaluate 1 by 7. You have to evaluate 1 by 9. You have to evaluate 1 by 11. You should get the values to 8 decimal place, 9 decimal place, right? The division has to be done. Then you have to sum all this. Then you have to subtract all this. Who will be able to do? It is humanly impossible. Okay. So Madhava has thought about, and then he felt that this is absolutely boring. So they have a nice term in Sanskrit, jamita. Okay. So jamita ho jayegi, isliye usko chhod denge. Okay, we leave this, we will find a different way. So that's what seems to have been done. So make an estimate of the, so you just sum up to something, and then you just evaluate what is going to be the contribution of the remaining terms. So that is a nice technique which they have evolved to get this. I am not going to get into the details of the mathematics as far as this is concerned, but I just want to tell you this is a brilliant analysis which has been done. Okay. So here, even if you just consider 20 terms in the series, so you will be able to get a pi value by employing this technique. You will be able to get a pi value which is correct to 8-9 decimal places. It's not a simple thing, really remarkable. The verses go like this. Yet sankhayatra harane nivritta hritistu jamitaya. I told you, no? Jamitaya hritihi nivritta. That fellow abandoned. I will not do any more. Then he says, Tasya urdhvagata ya samasankhya taddalam gunonte syat. See, it translates to this. So suppose you stop this at number p. Urdhvagata sankhya means p plus 1. Samasankhya. See, p is an odd number. All the denominators are odd numbers. So p plus 1 is going to be even number. That's why samasankhya, p plus 1. Taddalam means half of it. So he just says, this expression he gives you p plus 1 by 2, and the denominator tadvargo rupayutaha. Rupayuta means plus 1, haraha, and so on. So then he finally says, if you do the samskara, what you will get is far more accurate result. See, labdha paridhihi sukshmaha. Sukshmaha means more accurate. Okay, bahukritvo haranatoti sukshmasyat. Even if you were to keep on dividing and finding the sums, this will be far, far, far more accurate. How do you know that it is going to be accurate? This is an interesting discussion which is presented in the text. So we don't have time. I'll just tell you, Katham punar muhur vishama sankhya haranena asannatvam. How can you say that this is going to be much more closer? That is an interesting discussion. And I'll just tell you that the argument goes like this. It's a very, very simple argument, but very, very crucial argument. I'll just tell you. Suppose you have a series like this and you terminate at some point. Okay. This is the correction term. 1 by AP minus 2 is the Antya Samskara term, let us say. Then he says, you consider one more term. Suppose you stopped at, let us say, 21. then you go up to 23 in the denominator, and then you apply the correction term, right? So if the correction term were to actually make an estimate of the original series, then the difference of these two should be almost 0, right? If you have made an estimate of the remainder, you make an estimate at some other term, this difference should be 0, right? This is a simple argument with which they go. So then this has to be sort of 1 by p, okay? This should be same result. This is what it says. See, yadi tulyau bhavatah tarhi samskarah sukshmah iti nirniyatam. You yourself decide. Very nice argument. So then basically they try to do something, and you will do some error estimations, okay? You cannot make it same. You make some error estimate. You try to minimize the error. And what do you have? So you have something like this. So if you do the samskaras, then you just consider 20 terms in the series, okay, up to say 40, okay, 1 by 41 kind of a thing. So there are 2 orders in which you can do the samskara, and in the first order with 20 terms you will get up to 8 decimal places, 9 decimal places accurate, and in the second order you will almost get to 12 decimal place accurate. This is remarkable result which they have found. And so here is a manuscript, so which actually shows in Malayalam Lipi, see, one of the series like this, you see, Samapancha Hatayaha. See, once you do this correction term, you can further manipulate and express the same series in a different form. See, you express the same series in a different form, you see. But here what you notice is in the denominator you get all powers of 5, 7 to the 5. So as you move, so this is, you just incorporate those correction terms into the series itself and produce different brilliant series. So this is just to show you that this series is represented by this Samapancha Hatayaha, Ya Rupa Gyayujaha. See, Ayuja means odd number. Yuja is even number. Ayujaha. Okay. Ayujaha Chaturghana Mula Yutaha. You multiply all the odd numbers by 4. So this is the, then Tabhi Shodasha Gunita, see 16 times D Vyasat Prithagahrite Vishamayutehe. Vishamayuti means you sum all the odd numbers, sum all the even numbers, subtract one from the other. So this is how the series is presented. What is the nature of pi? So this has been nicely discussed by Nilakantha. He says, Paridhivyasayo Sankhya Sambandha Pradarshitaha. So he discusses the verse of Aryabhata wherein he has used the term asanna. Asanna means something which is close by. Okay. Why did Aryabhata say asanna? Why not give the correct value? This is the question that he poses. You give some rational approximation, then why do you say so? So this is an interesting question, and he basically goes to argue and then say, see, this can be taken like this, right? After all, you have some thread. Okay. So this thread, suppose you divide into 5 parts. So you get some remainder. You make it to 25 parts. You may get some remainder, right? But if you make it into 2500 parts, a small thread, you will not get remainder, right? Almost it will be same, something like that. So if you make the unit of measurement very small, then it should be possible for you to represent one, see, in terms of the other in integer itself, right? This is the question. So why is it not possible if you keep on reducing? So that's the question that he poses. So he says, see, so in Mahanta Madhvanam Gatvapi, even if you keep on reducing the unit of measurement, it will be almost impossible for you. See, he says, Alpavayavatvam eva labhyam. He categorically says. So there will be some remainder. Niravayavatvam kvapi nalabhyam. So this is what is incommensurability of the circumference and the diameter. This is a very interesting argument which is being presented in Aryabhatiya Bhashya. Now the last part of my lecture. I just wanted to tell you, because many of you would not have seen, this is like a slideshow, a few manuscripts. So how they are sort of maintained. So there are some manuscripts which are looking very nice like this. Okay. So something like this. So you will be able to see in various libraries how tightly they are written. You just notice, So it's not an easy thing to work on manuscripts. So the handwriting will vary. So now you see the third manuscript. These are all the equations. So in fact, so Amartya in his lecture was trying to explain, right, how the equations were represented, Yava, etc. So this is how you will see. So the lines, etc., are basically, if you just look at, see, he says, who, varga, varga, this dot, he was saying, right? This is negative things. So this is one of the Kerala manuscripts, which is in Malayalam Lipi. So myself and a couple of students, we used to sort of work on this. So the point I wanted to drive in was, so doing serious history of science is not an easy job. Even to decipher something from the manuscript and then present it is one tough thing. Then interpreting is a second level of thing. So it could be fascinating, but it would be really, really challenging and time consuming. Okay. Deciphering is a problem, content is a problem. Then, hi, what happened? Okay. So the point I wanted to convey was, it has come back. Very good. So it is a rewarding experience once you reach the light at the end of the tunnel. So it takes years sometimes. This is the last but one slide. So Donald Knuth, as all of us know, is a remarkable computer scientist who wrote the text, The Art of Computing. Okay? They are like Bibles, real fantastic texts. So he once says, in one of his talks, he says, my major failing as a teacher was I wasn't able to get a single one of my 28 PhD students to realize what a thrill it was to work with the source material. So that is one gets thrill, but it's a challenging thing. So the last part is there are so many things which have been, these are the various other modifications of the series. But then the reason I posed this question, right, could it be due to ignorance or could it be due to something else? We find that it is not necessarily out of ignorance. So this, when the series was first brought to the attention of the Western scholarship by Charles Wish, people could not digest the fact that this thing has been done here. And therefore, people have been saying, see, indeed, the pretensions of Hindus to such knowledge of geometry is too ridiculous to deserve refutation. So this is the kind of statement that has been made when this series, this Kerala work was presented. So the conclusion is, just a couple of points. So we have this interesting verse in Malavikagni Mitram, Puranamityeva, na sadhu sarvam, na chapi kavyam, navamityavadyam, santah parikshya, anyatarad bhajante, mudhav parapratyaya nera buddhi. So the point is we should not just simply abandon that this has been done 8 centuries ago, we have gone far ahead in science and technology. So that doesn't make much sense. So one has to really look into that. So one also has to be very, very careful. So praising something beyond what it deserves is counterproductive. Completely dismissing is far more counterproductive. So what one has to do is one has to just look into it. So as such. So this, based on my own experience of working in history of science for several years, at least a couple of decades, I must tell you that it is a rewarding experience. It is certainly not obsolete. We have many of us who have been teaching modern mathematics, we realize that there is something which is far more. What is interesting is the simple and intuitive ways in which some of the results have been arrived at by the ancients are truly astonishing. I just gave you one example of pi, and then there are several other results which can be highlighted. Even if there are better methods for understanding something, looking into the ancient provides us certain very useful insights. I can tell you out of my own experience, and it greatly facilitates understanding the development of the subject. So we would be doing considerable harm to our children if, while framing mathematics curriculum, so for which we have an opportunity now, if we do not pay attention to highlight any of them in the impressionable age. This is very important, and the teachers have to be properly trained for that. Making unverifiable claims or exaggerated claims is certainly unscientific. But what is scientific about suppressing or making uninformed statements or blind rejection?